Hello everyone, welcome back to ECE 3030. Before today's lecture, I'd like to have a few announcements. As you can see from the canvas, we posted an early stage feedback on the remote lecturing. So I would appreciate if you can take a few minutes to finish this anonymous survey under this quiz, so we can better change for the future lectures. And also the homework 1 is posted, and it's due September 4th, next Friday, 11:59 p.m. So basically it's midnight. And also I got a feedback so from some students, and here we posted the live session link and the YouTube channel link under the syllabus, so it's easier for you to navigate and then join those sessions or watch the videos easier. And also one more question is regarding the overall schedule of this semester. So if you recall, we have this lecture 0 on the administrative logistics. So under this slide, we have a tentative schedule. And I made one change here. If you look at the online version, the homework due was next Thursday before, but now I changed to Friday. So this will help you to fully utilize the weekdays office hour of the TAs. So this is the tentative schedule, and we'll try to follow this schedule. So you can see the homework out and due. And any other questions? I got one question from the chat. So the question is, for the homework, do you expect us to use LaTeX or just handwriting? I think handwriting is fine. So the homework, you can just, let's say, write down your solutions, and then, let's say, on a paper, and then you can scan it using some apps. Or if you have scanner, that's better. But if not, you can use your phone, and there are some app you can do the scanning, and then you convert to PDF and upload to the Canvas under the assignment. So here under the assignment, you should be able to see a link to upload your PDF. Any other questions? All right, so we can start our technical discussions today. Today we are going to discuss lecture 4, and this is again physics of semiconductors. And last lecture, lecture 3, we talk about the silicon crystal structure, and also we talk about the concepts like electrons and holes, and also the doping from the bond model perspective. And today we are going to talk about the same problem, but using a different perspective, and that is called the band model. And we will compare those two models later today, and eventually you will reach the conclusion that those two models are talking about the same physical picture. So today let's get started on this band model. And this is a reference chapter on the reference reading material. And again, this is a recording lecture from the last spring semester, and also from Professor Asif Khan. All right, so let's get started from the atomic picture of the atoms. So if you want to recall from your basic chemistry class, I know some of you may not be a great fan of the chemistry class, but let's do some review of the simple concepts here. If you think about atoms, so the atom will have a nucleus, and those are positively charged. And then around the atoms, you will have the electrons, and electrons will occupy on those orbits. And each orbit will have a corresponding energy level. So here we show the discrete energy level, and that will represent those orbits in terms of the energy. And the principle for the electrons to occupy the energy level is always to occupy the lower level first. So if you have some electrons of this atom, then electrons will tend to occupy the lower level first before they go to the higher level. And for those orbits from the lower level to higher level, they have different names, and like the 1s and 2s and so on. So those are the labels for the energy levels. So this is a basic picture for the atoms. And then let's look at a simplest atom, that is hydrogen. And hydrogen, you know, is just one electron per atom. So in the middle, you have the positive charged nucleus. And then for the hydrogen, because it's only one electron, it occupies this 1s orbit. So here we use this arrow to represent an electron on this energy level. And this arrow actually stands for the spin up of the electron. We will not talk about those details, what is a spin. But here, this is just a representation of the electrons with this spin up. And here the question is, if we want to form hydrogen molecule, what can we do here? So you know, hydrogen molecule, H2, means we are going to move those two individual hydrogen atoms close to each other. And if you do that, then those two hydrogen atoms will interact with each other. So here the energy level, 1s, will be split into two levels. And then the lower energy level is called the bonding level. And the higher energy level is called the anti-bonding level. And now the electrons will tend to occupy lower level first. So here the lower level will be occupied by those two electrons first. So those two electrons now will occupy the lower level first. And then this is to form this covalent bond between those two hydrogen atoms. And here we have this spin up and spin down. This is due to the so-called Pauli exclusion principle. And this is one of the principles by the quantum mechanics. And we will not go to the details of that. But basically it says that one level here can at most hold two electrons at the same time. So here you see that this lower level is occupied and the higher level is empty. And now we have the hydrogen molecule like this. So this is a covalent bond. Any questions so far? If you have any questions, feel free to unmute yourself or type in your questions through the chat. Alright, so once again, we have some notes under each slide, so you can review that after class. So here you may wonder why this is called the bonding levels, other one is called anti-bonding level. So the reason is that the electron tend to occupy lower energy level first, and then this forms a covalent bond. But if, let's say, the temperature is increased, so then the electrons may have enough kinetic energy to jump from this lower level to the higher level. Then this is anti-bond level. So essentially the bond is broken, and then the electrons are occupying the higher level. So that's why this is a two-level system in the hydrogen molecule. Why do we want to discuss this hydrogen molecule? The reason is that we want to use the same energy to be applied to our silicon crystal. And here, this is the bonding in the silicon, because we are interested in silicon in this class. But silicon is more complicated. As we know, for individual silicon atoms, if you recall the last lecture, we said that silicon has 4 shell electrons on the outermost orbits. So those 2 outermost orbits are 3s and 3p. Of course, you have lower orbits below that, but they are not going to be involved in the conduction of the current. So here we only look at the outermost orbits, 3s and 3p. And again, this is the electron's energy level, so 3s and 3p. So silicon has 4 shell electrons, and 3s will have 2 electrons filled. And as we discussed, this is because the Pauli exclusion principle. You can only have 1 spin up and 1 spin down, 2 electrons occupied by this level. And then 3p, you have another 2 electrons. And in total, 3p actually can hold at most 6 electrons. But in silicon, you only have 2 electrons there. So here you have those 2 electrons. But in principle, 3p can hold more. For example, if you go to number 15 elements in the periodic table, you have 3 electrons, because silicon is number 14. If it's number 15, you will have 1 more. But for silicon, you only have 2 out of the 6 available states in the 3p. So those are individual atoms configuration. Now the question is, what will happen if we want to form the silicon solid? And the silicon crystal may have many atoms. And as we discussed in the last lecture, the atomic density, right? So for silicon, that's 1 centimeter cubed volume may have like 10 to power 22 number of silicon atoms. So this is a very large number, and we use n, let's say n, to represent this large number in the silicon solid. And then if you have n number of silicon atoms, then in total this system may have, let's say, 2n available states in the 3s, because each silicon atom has 2, and you have n atoms, so in total 2n. And similarly for the 3p, you have 6n available states. So if you add those 2 together, in total you will have 8n available states. And the electrons here in total will be 4n, because each silicon has 4 electrons, and in total you have n atoms, so you have 4n electrons in total. So here is the information of the silicon crystal. And here we are talking about the silicon crystal. In total, you have so many electrons, 4n, and so many available states, 8n. So it's not fully occupied, as you can see here. Any questions so far? One question. So each level can at most hold 2 electrons. Yes, that is true here. So this is due to the so-called let me see, where is it? This Pauli exclusion principle in quantum mechanics. So we will not discuss the details of that. This is beyond the scope of this class. All right, so then let's go back. Now the question is, what will happen if you bring those silicon atoms close together to form the silicon crystal? Before you do that, those are individual atoms. Now you want to bring them together to form this solid, the silicon crystal. Then what will happen? So that's our question here. So we can use the same energy from the hydrogen molecule And this diagram shows what will happen. So here we have the, for example, your 3s and 3p orbits of the silicon. So here are the individual isolated silicon atoms. And we know that here we have the 2 electrons here and 2 electrons here. But here you have 2 n states. Here you have 6 n states available. So now as you bring those silicon atoms close to each other, so the interactions will happen, similar as what happened in the hydrogen molecule. So the energy levels now will be split into lower bonding level and higher bonding level. But here, since we have so many electrons and so many states, so this will no longer be a, let's say, discrete level. So then here you are going to create a band. Here's band means many levels, and there are so many levels because ideally, if you think one, here you have let's say 4n states to the lower band. So here you have 4n levels. Because n is a very large number, as we discussed earlier, 10 to the power 22. Then the spacing between those levels are so close, and we can think this is a continuous states. So we have this band. So here in total we have this 8n states, and then we are going to split that into the 4n states on the bottom, and then 4n states on the top. And in total we have 4n electrons here. So we have 4n electrons and 8n states. So after this split, then those 4n electrons, all of them will occupy on the lower band, and then this upper band is empty. So this is similar as the hydrogen case, as we see earlier, right? So those 2 hydrogen electrons will occupy the lower bonding level, and the upper anti-bonding level is empty. And in this case, it's the same thing. The lower band is fully occupied by those 4n electrons, and then this upper band is empty. And this is when you bring those silicon close to each other to this distance of the silicon lattice constant, as we discussed earlier in the last lecture. It's about like 0.5 nanometer. Any questions here? I got one question. Is the band a result of the hybridization of 3s and 3p? Yes, that's exactly correct. And we didn't discuss those details of chemistry here in this class, but that is correct statement. Any other questions? Then if not, let's go back. So here, this kind of band diagram is what we are going to use very often in this class. And here we redraw this. This is what we typically show. The arrow here means the energy level, and pointing up means higher energy to the top. So this is the electron's energy, electron energy. So in the silicon crystal, then we have those 2 bands. And here in between, we have so-called the band gap. Band gap means there's no available states for electron to occupy. Electron can only be in the lower band or the upper band. Electrons cannot stay within the band gap. Or in other words, electrons are not allowed to stay in these energy levels. And then here let's look at T equals to 0 Kelvin. This is absolute zero temperature. And as we see earlier, all the electrons, these 4n electrons, will occupy the lower band. So that means this is a field with 4n electrons, and then the upper band is completely empty. So we want to argue that in this condition, even you apply electrical field, there's no current flow. Why is that? Because all the electrons are in these field states, then there's no room for the electrons to move around. Then there's no flow, then there's no current. Or we can make an analogy to, let's say, if you think about the states as the seats in the classroom. Unfortunately, we are not in the classroom right now. But if you think that here we have many seats in the classroom, and the electrons is like a student. So if the classroom is fully occupied, then student A and student B exchange the seat. But in total, there's no net flow going on because all the seats are occupied anyway. So there's no current. So that's why here we reach the same conclusion as the last lecture. At T equals to 0 Kelvin, there's no current flow, and this silicon is more like insulator. Any questions? All right, so this is at T equals to 0 Kelvin. And then let's look at what will happen when the T is larger than 0 Kelvin. So this is when you have the thermal energy to the electron. So if the electron somehow get enough kinetic energy from your thermal source, then the electrons may jump from this lower band to the upper band. It cannot reach to the band gap because it's not allowed. So electrons can only jump from here to here. So this is to create an electron in the empty states. At the same time, then what will happen in the field states? You will leave a vacancy behind. This vacancy, as we discussed last lecture, is called hole. So here, electron and hole pair is created if you have thermal energy T larger than 0 K. So this is the free electron. And then if we have the electric field applied, the electrons will move opposite to the electric field. At the same time, the hole can move along the electric field. Now you have the net current flow. So then this silicon is kind of conductive. So here the electrons can move around because you see here so many empty states. It's like one student in the classroom. All the seats, you can choose whatever seats you prefer to sit, right? Then this can move around. So you can have the current. So here we are going to reach the same physical picture actually from those two models, this bond model versus band model. So let's do a summary here. Bond model versus band model. Actually, we are talking about the same physical process here. This is for the intrinsic silicon. Intrinsic silicon means pure silicon without doping, without those impurities. And in the bond model, what we discussed earlier is that when you have temperature, the thermal vibration may break the bond here. This is covalent bond between two silicon atoms. So once the bond is broken, then you create the electron and hole. It's a pair. And in the band model, we are talking about the same process. If you have thermal energy, the electrons can get additional kinetic energy. So the electrons can jump over this barrier from the lower band to the upper band. And so this is a free electron, and this is hole. So this is the same physical process, but two perspectives. And starting from this lecture to the future lectures, we are going to use a band model to describe this process. Because later, this band model, as you will see, will be easier to quantify some of those physical parameters. Any questions so far? I got one question. Does that mean there's current flowing in higher energy states? Do currents in different bands differ? Okay, I think you are talking about here. We say that if now you apply electric field, the electrons will flow in the higher energy band, and then hole will flow in the lower energy band. From the current point of view, doesn't matter let's say the electrons, where the electron is in the energy level, as long as the electron, from the current perspective, what you care about is how many electrons here and how fast they move. Those will determine the current. So no matter this electron current or the hole current, actually they are equivalent. If you can only look at the electron current here, then that will determine the total current. Or you can only look at hole current here, then that will determine the total current. But of course, now both of them can be moved. So the current will be the sum of this electron current and hole current. All right. We will talk about the current in more details, I think, in lecture 6. Okay, so let's go back here. And we want to answer one question. What is the difference between those different materials? Let's say metal versus insulator or semiconductor. And the insulator can be typically like a dielectric oxide. So we can look at the differences from the band diagram's point of view. So if you draw the band diagram here, band diagram means you draw this arrow, and then this is electron's energy. And then for the metal, the filled states and empty states overlap. So here you have overlap. So here overlap means the electrons can freely move, right? Because this electron will see those empty states available. So if you have electric field, these electrons can move around. So that's why it's very easy to conduct current. So this is a metal. And then for the semiconductor, as we discussed, we have this band gap between the filled states and empty states. Similarly, in the insulator, for example, oxide, we can also have this band gap. The only difference is that the band gap Eg, we typically use Eg to represent the band gap. The Eg is different. The value is different. So for the silicon, it's a semiconductor, and the Eg is 1.1 electron volts. And then silicon dioxide is an insulator, and this band gap Eg is about 9 electron volts. So there's no clear boundary between semiconductor and insulator. You can say that insulator has a higher energy band gap, but it's hard to differentiate that using a clear boundary. So in practice, people typically define when the EG is 4 electron volts, it's kind of the boundary in between. So that means above 4 electron volts, then it's more like insulator, and below the 4 electron volts, then it's more like semiconductor. So by the way, here electron volts is a unit for energy, and this is what we typically use in this class when we talk about the semiconductor physics. We typically use this as the unit for the energy. So by definition, electron volts is 1 electron which carries like 1 volt, or you apply 1 volt on the electron. That is the energy. If you want to make the electron carry 1 volt, then the energy to do that is 1 electron volt. So 1 electron times 1 volt. And if you want to convert to the SI unit, then you need to do it this way. So 1 electron, so then electron's charge is a physical basic quantity is 1.6 times 10 to negative 19 coulomb. So this is the charge on the electron, and then you need to charge this by 1 volt times 1 volt, and then you will get 1.6 times 10 to negative 19 joule, and this is SI unit for the energy. In this course, we will keep using the electron volts. Any questions here? If not, then I'll stop the recording of this session.